everyone sticking around. So my name is Christoph Sydora. I am a postdoc at the University of Alberta in Canada. And the presentation I'll be doing is on learning interior design rules from user-created layout examples. This is a small part of my PhD thesis, and in that thesis we were kind of interested in two automation tasks. So the first of which is the idea of, you have a layout, you had a set of design rules that you're interested in, and you want to evaluate your layout based on those design rules, so getting sort of a checklist. And then the other one that we were interested was taking that step further and looking at an empty layout. You have a set of furniture that you want to put within that layout, and then you again have the set of design rules that you want that layout to comply with. So then it's an iterative process, and then you eventually get the layout that you want and some degree of compliance with that layout. So in both these cases, you need to have, if you want to automate the tasks, you need some kind of computer representation of those rules. So that's what we're going to be focusing on. So historically, the way you would have done this was you look at your design rules, and you either hire a programmer or you program it yourself, and you then convert that into a general purpose programming language. So what we worked on up to now has been on a development of a domain-specific language for describing those interior design rules at a higher level. So that's a little bit easier for someone who doesn't exactly know programming as they're very well, and that compiles down then to a machine-readable format. So for this project, what we wanted to do is even take that a little bit of a step further and see if we can extract those design rules from just examples. So just briefly, so we're saying that we're learning machine-readable geometry rules from those examples. So I'll just quickly mention some related work in the area. So there are other ways of extracting knowledge from examples. So we haven't really exactly seen anything in terms of producing like code from examples, but there's a lot of different methods that capture some kind of design information from those. But generally the usage of those has always been you just give examples, you have some kind of black box, and then you produce something that looks like the examples, but nothing in terms of an evaluation of how well those met the rules or anything like that. So our approach kind of addresses that by kind of opening up that black box a little bit and making it a little bit more explainable. So I mentioned the DSL, and I'll just kind of briefly say what the rule language is. So we're calling it rule DSL. The idea is that it's a very easy language to understand because it uses domain-relevant terms that a designer will understand. It's expressive enough to capture geometric rules that we're interested in. And just like I mentioned that because we're using this for a generative design process, it really helps to have these sort of search gradients. So instead of just a pass or fail for each of those rules, we're interested in something that gives us a degree of pass or failure. So you know that you're kind of approaching a pass by moving something in a certain direction. And then lastly, I'll just mention from a development standpoint, so this is part of what we're calling BIM kit, which is a broader toolkit of apps and services that help kind of make this more extendable, and also includes some rule editing capabilities. So I'll just kind of give a very high-level version of the rule learning algorithm. So I'll give an example here with generating bed and wall rules. So the idea is pretty straightforward. You observe a certain number of geometric relationships that you're interested in. And then the idea is that we have these like one-to-one and one-to-many relationships between these object types. So in this case, if it's the all-to-all, like a many-to-many, you just look at all of the relationships and you kind of create a range of acceptable values to capture those the observations. So we do that for one example, and we kind of do that by combining, again, these one-to-one and one-to-many relationships. And then, we have a bunch of candidate rules, we call them, which are essentially all valid potential rules that you could express or capture from the one example. And then the idea is to then look at all these candidate rules from various input layouts, and then we combined all those candidate rules by just doing an outer bound or outer join of all of the relation ranges that we observed. And then we also have a rule reduction phase. That's just very briefly, like there's a lot of duplicates sometimes, or you have supersets of other rules, so we can just eliminate a whole bunch, and that way we're not getting, the number of candidate rules aren't ballooning out of control. And then finally, we repeat that process for each new example that we introduce, and then eventually you get a final set of candidate rules, and then we convert that back into the rule domain-specific language. So like I said, the goal was to extract these rules from the examples, but of course we want these rules to capture some kind of implicit design knowledge. So the way we're going to test that is by taking those rules, and then we generate layouts using those learned rules as evaluations. And then the idea is we compare those learned layouts with the input layouts, and if they're of the similar quality, then we must have captured some kind of implicit design knowledge. So the way I'll just kind of mention the room scenarios that we're looking at here. So we looked at 4 different room types, so living rooms, kitchens, bedrooms, and bathrooms. And we kind of changed the complexity of each of these by changing the shape of the rooms, and we also looked at different densities. So that's just like adding more or less objects. So we had 9 room scenarios in total. And the first part of the study was we got a bunch of participants. So we got about 18 people to come in. All they had to do was create these layouts. So we gave them an empty layout. We had a bunch of furnishing items. They just had to put them within the room. And then we also asked them whether or not they felt that they were an expert in design or not, just if they had any kind of formal training. In the end, we had pretty much all of them said they weren't. So the quality of the layouts wasn't exactly up to par. But yeah, that was just kind of a limitation that we'll get to later. So once we had those layouts, we ran them through 3 different versions of the rule learning. So the first version is just taking those examples and only learning from 2 of them, learning the rules, generating new layouts from those rules, and then we did that for there are 2 input layouts, for 5 input layouts, and then we did it once for all 18 layouts. So what we did then was we had a website where we had a new set of participants that could go on that website, look at all the user-created ones and all the learned layouts, and they could evaluate those on a scale from 1 to 5, 1 being that it was an absolute mess and there's nothing usable in there, and 5 being that there's a lot of excellent design choices and there's nothing wrong with the layout. So we had about 120 people go on that website and evaluate the layouts, so that means that about every layout got about 56 evaluations just for statistical significance there. And then, yeah, just going through the results really quickly here. So the humans scored about roughly between 3 and 4 on a scale of 1 to 5, so they weren't exactly the highest quality layouts in the end. And when we learned from only 2 of those layouts, we get some that are roughly the same quality as the input human layouts, but when we start increasing the number of layouts from learning from 5 and learning from 18, the quality of the rules learned and therefore the learned layouts really significantly decreased. So that was kind of the end finding for that. And I'll just kind of give some quick interpretation and discussion for that. So the first thing was, once, as we showed, once you increase the number of input layouts, you get a lot more variability, and just because of the way the method was set up, the more variability you get, the wider these ranges of acceptable values gets, and then you kind of get into this area of, well, anything's acceptable, right? So that was kind of one of the big takeaways from that. The second one was we didn't really control for the quality of these layouts, so a lot of these users, when we asked them, like, why did you make the decisions you made, a lot of them would just say, I don't know. Like they were very unclear of it, which is kind of a motivation of the whole thing in general, is because we want to capture this implicit knowledge. But yeah, it was very hard to like get any kind of assessment of like what the actual quality of them going in was, and they weren't exactly experts, so they weren't following any kind of rules. And then finally, the rule language is a lot more expressive than the template that we kind of constrained it to. So we looked at distance, facing, and alignment just because we figured those were the most important ones, just looking at literature and looking at all these design rules. But there's a lot more that we have available, a lot more geometric relationships we could look at, and we could also increase the complexity of them. So that's something that's, I think, we're going to leave for future work. So I'll just reiterate the contributions here. So the first is we developed a method for learning and extracting machine rules from examples. We had a collection of layouts that we got from participants, and then we evaluated the method's output rules through this survey. So I'll just mention the acknowledgements here, and everything was above board with ethics. And yeah, thanks for participating or attending.
Thank you very much, Chris.